All right. Hey, class. We're going to go over lecture 27 now on reaction rates and get kind of an intro to that and talk about reversible reactions. And one thing I wanted to point out, at this point, we are about 4 lectures away from the next exam. The next test is August 3rd and August 4th. Again, it's a Monday and Tuesday, so kind of the same pattern that we've seen. And again, I'll post exam review, so it should be very similar format to the last 2 exams. And then after exam 3, there's only 5 more lectures until the final exam. So 5 more lectures, we cover that in a week basically. So then most of the exams have been a week apart, and I think from exam 3 to the final exam, I think there's like 10 days. Let me just check. Yeah, it looks like the final exam is scheduled for August 13th. So it's about a little over a week after exam 3. So it's kind of going to be a fire hose at the end here, getting stuff done. So we are very close to the end of this very short summer term. And as a reminder, I will drop one of the lowest exam scores, but the final can't be dropped. So out of exam 1, 2, and 3, the lowest will be dropped. The final isn't dropped though, so just keep that in mind. And yeah, so it's important that you're reviewing exams and making sure you're understanding what you missed instead of just brushing it off, because all that stuff will show up again on the final exam. And you can kind of tell that things build upon each other. For example, if you didn't understand Lewis structures in the first exam, you would have you probably did struggle on that portion in the second exam, or naming compounds and stuff like that. That's all pretty basic that I kind of just expect you to know at this point, or polyatomic ions and stuff like that. So, all right, let's move into lecture 27. Okay, let's go ahead and start out with this review quiz from the last lecture. All right, so the question says, what happens to blood cells in a hypotonic solution? Okay, so again, remember hypo should signify less. So what that would say is that you would have a less concentrated solution outside your blood cell. So if it's less concentrated, then you're going to be having water move into the blood cell, right? Water moves from the less concentrated to the more concentrated side. And the way to remember that is you're trying to get the concentrations equal. And so in order to do that, you need to lower the concentration inside the cell, and you do that by adding water to it. So water would enter the cell and it would swell up, okay? So know what happens in a hypotonic, hypertonic, and isotonic solution there. Okay. All right, so we're moving into reaction rates. So as a quick review, we've talked about activation energy, right? So when a reaction happens, the first step is the bonds need to break between the already existing molecules. And the energy that's required for that to happen is your activation energy. Okay, so that energy brings the reaction up to here. And then new bonds are formed, and that releases energy when the new bonds are formed. So just the energy required to break the bonds is going to be the activation energy. And we're going to talk a little bit more about the theory, what really needs to happen. So molecules, again, they're always constantly moving, right? If there's any amount of temperature above 0 degrees Kelvin, the molecules will be moving. And so in order for molecules to react, they need to collide into each other. And when that happens, they need to have enough energy on the collision. So imagine like, I don't know, like a bike running into a wall versus like a car running into a wall, right? The car is going to have a lot more energy when it hits the wall. So the molecules need to be going fast enough or have enough energy when they hit that the bonds, the existing bonds break, okay? And when that happens, the existing bonds break, and that's the activation energy. And then new bonds form, and that's where you gain back some energy. Just a few things that just need to happen though for a reaction is the molecules must collide. They must have enough energy when they do collide to get above that activation energy barrier. And they need to have the correct orientation, right? So just the bonds breaking doesn't necessarily mean they're going to form a new compound. They need to break and collide in a certain orientation so that they're set up for the new bonds to form. So really, I mean, what I really want you to know from this is just that you need enough energy and the molecules need to collide in a correct orientation for the reaction to happen, okay? All right. So reaction rate is going to be the speed at which a reaction happens, okay? So if you have A plus B coming together to form a molecule AB, right? The speed at which the reactant is used up, so the speed at which this goes down, and the speed at which the product is created, this is referred to as the reaction rate, right? Pretty self-explanatory, hopefully. But there are a few conditions that will either speed up or slow down the reaction rate, okay? And we're going to talk about those. There's 3 conditions that you'll need to know. So first is concentration. So if you remember that molecules need to collide in order for the reaction to happen. If you increase the concentration of reactants, it increases the number of collisions or the probability that those molecules will run into each other. So if you look at this, if you just have one blue ball and one red ball, right, there's one possible collision for those two. If you have 2 blue balls and one red ball, then this ball could collide or that ball could collide. And so it gives you more possible collisions, right? There's more number of collisions. So more collisions is going to be a faster reaction, okay? Another way to think about it is like if you have molecules that are, if it's really low concentration, the molecules are really far apart from each other. So they're traveling around in solution, and the probability that they will hit each other is a lot lower if there's a lot more space between them. If they're all crammed together, then they're going to be running into each other a lot more often, and the reaction will be happening faster. So increasing the concentration increases the reaction rate. Okay. The other part, key part of a reaction is having enough energy, right, for the molecules to collide and for the bonds to break, right? This is referred to as the activation energy. So there needs to be a certain amount of energy in a reaction in order to provide enough energy for the reaction to come up to this point. So if you have a higher temperature, that means there's higher kinetic energy, right? So there's more energy available when the molecules collide. So if there's more energy, then it's more likely that you're going to climb up this activation energy hill. And so that also increases the reaction rate. Okay. And then catalysts. You may have heard this term before, but what it really does is it lowers the energy of activation. So if this blue line here is like what the normal reaction is, whatever, let's say you're doing A plus B again, takes you to AB, okay? Normally, you're gonna need this much activation energy for this reaction to happen, okay? But if you add a catalyst, then it creates a different reaction path that allows you to do the exact same reaction, but it only requires, you know, in this example, about half the energy to do the reaction. So it kind of has the same effect as, well, it doesn't have the same effect, but what it does is it speeds up the rate of reaction because you're lowering the energy required So you have this pool of energy, and you're increasing the likelihood that the collisions are going to happen. It also improves the orientation. So catalysts sometimes help order the molecules so that they're in the correct orientation for the reaction to happen. Then one other characteristic of catalysts is that they're present at the beginning and the end of a reaction. So one catalyst can help multiple reactions happen because it stays the same. The reaction gets used, and then, the catalyst gets used to do a reaction and then gets used to do another one. So you often, let's say you have 100 A molecules and B molecules, you may only need one catalyst to convert all 100 of those into AB. So that's just an interesting fact. But in summary, really what you need to know from all this is to increase the reaction rate, or to speed up a reaction, you can have a higher concentration, a higher temperature, or add a catalyst. And then the opposite is going to be true. Lower concentration, lower temperature, or no catalysts are going to slow down a reaction. So that's really all you need to pull from that first part. And right now we're just kind of getting a introduction, or an introduction into this stuff. So keep it pretty simple for now. Okay, go ahead and pause the video and try and take this quiz. Okay, so the quiz says, what happens to the reaction rate over time? Okay, so imagine you're doing, I think the easiest way to think about this is, let's say you start with A plus B at a concentration of 0.1 molar of A and 0.1 molar of B, right? And we're going to A plus B, or sorry, we're going to be forming AB. Well, after some time, let's say half of this reaction happens, then your new concentration would be 0.05 molar and 0.05 molar, right? So after some time, your concentration of reactants has lowered. And we learned about what happens when we lower concentration, right? If we lower the concentration, which happens over time, then we get a lower speed, right? A lower reaction rate. So it should slow down the reaction over time, okay? Awesome. Okay, so we're gonna get into this idea now of reversible reactions. So far, we've always looked at just a reaction as like A plus B gives you AB, right? Or like lead oxide decomposes into lead plus oxygen or something like that. We've just looked at one way. But reality is that I don't know if most, but many reactions are reversible. So they're actually happening in both directions all the time. So for example, take this reaction. Normally we'd see something like this, where nitrogen oxide, two nitrogen dioxide molecules would combine to form dinitrogen tetroxide molecule. And so we've always just thought, okay, you put these together, it's going to form this. Well, the reality is, at the same time that you're forming this, some of the dinitrogen tetroxide is going to be splitting back up into nitrogen dioxide molecules. So the way that we're going to look at this going forward is you'll see a double arrow when it's a reversible reaction, okay? So if you have a reversible reaction, you'll see this double arrow, and that means that this reaction is happening in the forward direction, and we're also having some reaction happen in the reverse direction. We're going to talk in future lectures about how to tell which one is more prominent, right? So generally reactions are written in the way that the forward reaction is happening more. So each of these reactions has a individual kind of like reaction rate. And so sometimes the forward is favored over the reverse, or the reverse is favored over the forward. Don't worry about that right now. Right now we're just learning what these are, and in the coming lectures we'll talk about like how to tell which one's favored and stuff like that. Okay. All right, go ahead and try this quiz here, see how you do. Okay, so the question wants us to write the forward and reverse reactions for the following reversible reaction, okay? So if we looked at just the forward reaction, so just methane plus hydrogen sulfide, dihydrogen sulfide, going towards the right, we're going to create carbon disulfide and hydrogen gas, right? This is the forward direction of that reaction. The reverse direction is just taking the products, making them look like reactants, and drawing them, converting into the reactants, which now look like products. So anyway, again, I just want to get you comfortable with the idea that when you see this double arrow, you're saying that two reactions are happening, okay? You're getting a 2-for-1 deal right here. Okay. And so here's what's happening at chemical equilibrium. So as soon as a reaction starts, so let's say we're looking at this reaction where A plus B forms AB. Well, let's say this is actually a reversible reaction. So when you start the reaction, you're just going to add A and you're going to add B. I think it's raining outside. It's like really loud. Okay, sorry. I haven't heard rain in a while. So if you add A and add B, the only reaction that's going to happen is A and B convert into AB, because at the beginning of this reaction, there is no AB initially, right? So this red line shows the rate of the reverse reaction. At the beginning of the reaction, that rate is 0 because there is no product to go in the reverse direction. But as you create product, that rate starts to go up, right? As the concentration of AB goes up, the rate of reaction in the reverse direction goes up, okay? So if we looked at the forward reaction, maybe it'd be helpful if I separate these. Forward reaction looks like this, and the reverse reaction looks like this, okay? So initially, we're starting with just AB. So this has a high concentration, so we have a high rate of reaction. But as we form AB, that rate's going to go down because our concentration is lowered. And the red line shows this reaction, where we start with basically 0 AB, so the reaction rate is 0. And as your forward reaction creates AB, that reaction rate is going up. Okay, hopefully that makes sense. There's going to be a point at which these rates actually equal. Okay, they're going to come to a point that we call equilibrium. And that means that the rate of the reverse reaction is going to equal the rate of the forward reaction. So when they start, one's really high, one's really low. This one starts to drop and this one starts to go up. And they're going to come to a point where they're equal. And that's what you call like chemical equilibrium. It doesn't mean that the amount of AB and A plus, it doesn't mean that the amount of A and AB are equal. It just means that the rate at which AB is created and the rate at which AB decomposes is the same, okay? We'll get to that a little in this next slide. Okay, so in this last graph, this says reaction, okay, my line is great. This says reaction rates, okay? So the reaction rates come to a point where those rates are equal to each other. The concentration, which we see in this graph, okay, we're showing equilibrium again here. So we talked about how the reactants are going to decrease and the products increase over time. And you see that at equilibrium, the concentration of products is higher than the concentration of reactants, right? We'd expect that. So the difference I want you to know is that the concentration. So at equilibrium, the concentrations don't have to be equal. They can be a different number. The only thing that's equal at equilibrium is the reaction rate. So the forward and the reverse reaction are happening at the same rate. And if those reactions are happening at the same rate, then the amount of product and the amount of reactant are going to remain constant throughout equilibrium because they're happening at the same rate, okay? So another way to look at equilibrium is when the concentrations stop changing, okay? All right, spend some time, if that didn't make sense, I don't know, spend some time trying to wrap your brain around how the rates are the same, but the concentrations are different, okay? But the concentrations are constant. They're not necessarily equal, but constant, okay? All right. Let's go ahead and try this quiz real quick. Okay, so the question says, why do the reactant and product concentrations stop changing at equilibrium? Okay, and so forward and reverse reactions stop occurring. That's not true. The reactions are always happening, okay? The molecules no longer have enough energy to get over the activation barrier. That's also not true because if, as long as the temperature remains constant, so let's say the temperature is like 100 degrees Celsius or something, if it initially had enough temperature or energy to make the reaction happen, as long as that temperature is constant, it's still going to have enough energy to do the reaction. And the reaction is happening, right? Even at equilibrium. See, the rate at which reactant and product molecules are formed is the same. That's true, right? So at equilibrium, that rate is the same. And so since the rate is the same, the concentration remains constant. So C would be the correct answer. D says the reactant and product concentrations are now the same, which again, that's not true at equilibrium. The concentrations don't have to be the same. It's just the rate that remains the same. Okay. All right. Let's see. So this little note here that explains the answer a little more says, or let's imagine over the course of 1 second, the forward reaction uses 5 moles of reactants. So that rate would be like 5 moles per second. And the reverse reaction produces 5 moles of reactants. So the rate in the reverse direction is going to be 5 moles per second. So you can see that products are being created just as fast as they're going away. But since that rate is the same, then the concentration doesn't change. Okay, I've said the same thing a lot. Hopefully it's starting to click a little bit. All right, that was a pretty short lecture. I'm just giving you a quick introduction to reaction rates, and we're gonna dive a little bit more into like some math and some numbers and talk a little bit more about the significance of those moving forward. So, all righty, we will see you in the next lecture.